Fine. We discussed about the last class latches and flip-flops. In that flip-flops, how we are using different type of flip-flops, and then synchronous and asynchronous flip-flops, latches, all these things, right? Okay. So what is the difference between the synchronous and asynchronous, and difference between the combinational and sequential? All these things we have discussed. And then now today we will discuss about the registers. So group of flip-flops is called as a registers. Okay. So we are see flip-flop is a single bit storage device, right? So whatever the flip-flop you are considering, that is one bit storage device. So these one bit storage devices you can form a register. Okay. So that means you want n bit register. Okay. How many flip flops are needed means n flip flops are required. Okay. So because it is stored in the binary format of data, whatever the binary format of data, that is 1 0 1 0 1 0, this binary data only it is formed. Suppose here 6 bits I have formed, then all the 6 bits are stored in 6 flip flops. Then this is a 6 bit register. Okay, suppose I want to form an 8 bit register. Okay, so just I want to place that 8 bit values here. Okay, 1 0 1 1 0 1 1 1. Okay, so then all 8 bits are stored. Then here the data will be stored in the data will be also moving from left to right and right to left. So these registers are classified into different modes. Okay, one is called serial in serial out register. In this serial in serial out we have two types. One is right shift register and other one is left shift register. And one thing, serial in parallel out. Okay, so serial in parallel out, parallel in serial out, and parallel in parallel out. So four types of registers are available, so we will discuss one by one. Okay, these are the basic movements of shift registers. See how the data is moving from right to left. So this is the uh, right to left and left to right. So this is left to right shifting. That means right shifting the data. Suppose 1 0 1 1 data is there. Okay, this one is coming out, and then this one is moving this place, and 0 is moving to this place, and 1 is moving to this place. This is the empty position. This empty position is replaced with 0. Okay, so that is the one thing, shift operation. This is the shift operation. Similarly, ROR, rotate right. Okay, so rotate right, and then uh, see here we are rotating right. So ring type rotation, and then whatever the outside bit is there, that will be replaced with MSB position. Suppose 1010 is there, right? 1011, then 101 is the answer here. Then this empty position is replaced with outside bit. Okay, that is rotation right. So that means rotation operation, rotate right and rotate left is there, right? So that is the rotation operation, same shift operation only, but shift operation, that MSB bit position is replaced with 0. But here the MSB bit position is replaced with whatever the bit is coming out from this register. Okay, either 0 or 1, that bit will be replacing here in the MSB position, that is vacant position. Okay, similarly, left shift operation. So same type of operation, 1011. So the bit is moving to left shift. Okay, so remember the right shift I told you in, I think yesterday. So whatever the data we have, 1010 data. So this is right shift wave 1. That means the remaining bits will be, what is the values here? 0, sorry, 1 0 1. This empty position is replaced with 1 here. Then what is the value here? 5. Okay, so whenever we are shifting by one right shift, that is divisible by 2. Okay, the value is divisible by 2. Okay, every time you are shifting the right means you will get the half of the whatever the value you are giving, that will be half. Okay, and then left shift operation. Okay, this is what is the value, 8 4 2 1 code. So 8 plus 2 10, 10 plus 1 11. Okay, if we are moving left side, okay, this one is replacing here, and 0 1 1 here, we will place 0 here. Okay, so what is the value here? We got 11, right? So the value is 11. 8 plus 2 plus 1, that is 11. Here, every time you are doing the left shift operation by 1 means, okay, it is the value is multiplied by 2. Value is multiplied by 2. Every time it is multiplied by 2. Okay, one left shift operation you done means that is one time you should multiply it, and two times you done that left shift operation means, so you need to multiply with 4. That means n times you will shift it means 2 power n times you need to multiply that value. Okay, so that means every time you will get 2 power 0, 2 power 1, so 2 power 2. That means 2 power 0 is not available here because already one shift is there means multiply by 2. That is 2 power 1, 2 power 2, and 2 power 3. So 2 power 4. In this way we will get that answer. Okay, so just take any register and then left shift by 1, then you will get powers of 2 value. Okay, and then here the data, how it is coming out, I will explain in the next slide. See here, parallel in serial out. That means you are giving the input parallelly, all the inputs are giving parallelly, but output will getting serially. Okay, so that is parallel in serial out, and serial in parallel out. So you are giving serially, every time I am getting the output here. Okay, so that is serial in parallel out. Parallel in parallel out means at a time, single clock cycle, all the signals are coming out whenever you are giving the input, and at the time only I am getting the output here. Okay, and rotate left, I told you rotate left means from the right side to left side to right side. This LSB bit position is replaced with coming out bit, either 1 or 0, whatever the bit you are coming out from the register. Okay, that will be placed at LSB position, that is rotate left. Clear? See, serial in serial out register, that is left shift operation we are doing that. See, every time initially all the values are 0 here. That is Q3 is 0, Q2 is also 0, Q1 is also 0, and Q0 is also 0. That is the initial condition. Okay. After that, whenever I am giving the data value 1 here, then D0 will be 1, then Q0 will be 1. So Q0 is only 1, and remaining Q3, Q1, Q1, Q2, all rest of the flip flops are 0 maintained. Okay, all the flip flops are 0 only. And then after that, giving 1, I am giving another 1. This bit is moved to D1. That means output of Q0 is connected to D1 here. Then D1 output is Q1, then Q1 output is 1 here. After that, Q0 output is also 1. Still Q2 and Q3 are 0 only. Okay, so then still Q2 and Q3 are 0 only. After that, again I am giving 1 here. Okay, so that means another 1 I am giving here, that this one is moving to Q2. Okay, Q1 output is moved to D2, and then output is Q2 getting. Q2 output is 1 I am getting here, and Q1 output is 1 here, and Q0 output is 1 here. Okay, so and still Q3 will be 0. Up to these three clock cycles are required here, and then fourth clock cycle, all the data will be loaded here. Okay, so then Q2 output is moved to Q3. So then I am having all ones in this register, 4-bit register. then I need to get all the outputs serially. So again another clock signal will give that. Okay, so then this q3 and q2, q1 and q0. Q3 is 1, q2 is 1, q1 is 1, q0 will be 0. And again this output will coming out. Okay, this one and 1 0 0. Again one output is coming here. Okay, this is one output and then three outputs and sorry, two outputs here, and then 1 0 0 0 again. So one another one I am having. Okay, so then 0 0 0 0. Okay, see, all ones are four ones are coming out. This is my output whenever the data is given here, and then all the data output is coming out here. How many clocks are required here? 1 2 3 4 5 6 7 8. So generally this eighth clock all values are 0. That means 2n minus 1 clock cycles are required here. Okay, so that means 4-bit register you are taking 4-bit minus 1, that is 8 minus 1, 7 clock cycles are required here. Clear? How the data is coming out from the serial in serial out register?
I have one question.
Huh.
When to decide will be left shift or how to decide if it will have the left shift or right?
Based on the design here, see here I am doing the design like this. See, from the right side I am placing my d not flip flop. Okay, so then this is the lsb position, and then here it is moving to second shift register, and then you can see the right shift operation means, see that d naught will be placing here, d1 is here, and d2 is here, and d3 is here. Okay, the data is giving for the d naught, and then d naught will be connected, q naught is getting out, and that is connected to d1, and q1 is connected to d2, and d2 output is q2. So this q2 output is connected to d3 and q3. See how this connection is going on from left to right, that is right shifting operation is doing here. Okay.
Yes.
See, and then here the first output of flip flop is connected to second one, but it is moving to left side. Okay.
Yes.
The connection you can see here. So how the flip flops are connecting? This is the D3 means this is D2 and this is D1. This is D naught, and then connection is reverse. Okay, connection is reverse, that is right shift operation. Okay, and here the values are changed here, d3 to d naught, and d1 to d2 to d1, and d2 d1 to d2, and d naught to d3. So the values are increasing from right to left side. Okay, then it is left shift operation. Clear?
Mm. Mm.
Similarly, same thing.
Yes.
How it is data is moving, right? So first clock cycle, second, so four clock cycles are required. After that, remaining three clock cycles, the data will be emptied. That is the right shift operation here. How it is doing that? First, I am giving 0. After that, 1. After that, 1. So then 0. Then 0 double 1 0 is loaded. That will take 4 cycle. After that, coming out from that data, so that is also taking 4 cycles, and then first cycle is not required to consider here. That is, sorry, last cycle we are getting that coming out the data. That cycle is not considered. Then 2n minus 1 cycles are required to complete out from the data of serial shift register. That means serial in serial out register. 2n minus 1 cycles are required. Okay. Clear? Same thing. Here also I am giving the data here 0. Then my Q3 output is similarly Q3, Q2, Q1 and Q0. Initially all the outputs are zeros here. Okay. So whenever I'm giving 0, all flip flops are 0 here. This is the clock signal. Okay, so here we can mention the clock. This is first clock, and this is the output. I can mention all are zeros. And again, I'm shifting to 1 here. So clock signal is 1. So then Q3 is 1, Q2 is 0, Q1 is 0, Q0 is still 0. And the next clock cycle, second clock. So this is the first clock cycle, and second clock cycle, third clock cycle, and then here the next bit is also 1, 1, 1, 0, 0, and fourth clock cycle 0, double 1, 0. Okay, this is loading the data. Here loaded the data. All flip flops are having the data here 0, double 1, 0. Okay. So then in the fifth clock cycle, if you coming out from this data, okay, then here what is the data I'm having? I'm getting the output is 0 here, and then 1 is shifting here, 1 is shifting here, 0, and again 0. This is fifth clock cycle. And sixth clock cycle, 0, 0, 1, sorry, 0, 1. I'm getting 1 here. And then seventh clock cycle, 0, 0, 0, 0, 1 here. Okay, so then whatever I am getting output here 0 double 1 0. Okay, so that is the output. Say in the 8th clock cycle all are zeros, right? So then I am getting 0. So then whatever the data I am having, that data will be coming out from this serial input serial output register. Okay, so based on this states output, whatever the Q3, Q2, Q1, Q0 is there, based on that we will decide that is that output coming out fully from the registers or not. Okay, this is serial in parallel out. Input I am giving serially. Okay, just 4 clock cycles are required to complete all the data coming out from that. The number of clock cycles are required to load your data into the data is 4. Okay, 4-bit data is loaded into the data. Whenever loaded the data, at that time only I am getting the output, because serially I am giving the data. So 0 I am giving. This 0 will be coming out here, and then here 0 will be, Q3 will be, QB will be 0, and QC will be 0, and Q0 will, QD will be 0. Here QA will be 0. Then I am giving 1 here. This 0 will be moved to QB. Okay, this 0 will be moved to QB. Okay, this is 0, and then here 1 I am getting. Then my output is 1. After that third clock cycle, 1 I am giving here, and this 0 is moving here. Okay, again 0, and this 0 is cancelled, 1 I am getting here, and then here I am taking 1 again, double 1 0. Still QD will be 0 only. Whenever I am giving the 0 here, then this 0 will be placed here, and this 1 is moved to here, and this 1 is moved to here, and this 0 is moved to here. Okay, then all the data will be loaded at a time. I am getting the output also. Whenever the data is loaded, my data output is coming out, because parallelly I am considering the output. Okay, so these all are synchronous. How I am saying that? This clock will be every flip flop I am having the clock. Okay, serial in parallel out. Okay, and then parallel in parallel out. At a time I'm giving all the data, so same output I'm getting the output side. Okay, whenever you are loaded the data 0, 1, 1, 0, you are loaded. At a time I'm getting the data here 0, 1, 1 and 0. Only one clock cycle is required. Okay, only one clock cycle is required to load all the data bits. Okay, for serial in serial out, to load all the data bits, how many clock cycles are required? 4 clock cycles are required. Okay, for loading the data. For loading the data, so how many bits are there? So 4 bits are there means 4 clock cycles are required. And then serial in parallel out also 4 clock cycles are required, because I want to load the data. But coming out from the data is one cycle is required at a time. Whenever the fourth clock cycle is loaded the data, at that time only I'm getting the output. Okay, that is parallel in parallel to only one clock cycle. Whenever I'm giving the data, then only I'm getting the data. Okay, so parallel in serial out here, parallel in serial out, how the data is coming here? We are giving the data parallelly, that is loading option. If you give the load 0, then data will be uploaded here. Okay, the data will be loaded here. Whenever you are giving 1, then all the registers, see, because all the registers are parallel, right? Sorry, parallel input, right? So this is my register and this is another register and this is fourth register. Parallelly I'm giving the data. Okay, but my output is coming serially. Okay, how it is coming serially? See, this is the condition. How the data is coming serially. Parallelly, I'm giving the data input. So this is the D naught value. Okay. So this D naught is giving here, and then I'm getting the output serially. Then here two operations we are doing. One condition is 0. Okay. 0 is giving here. Then 0 is passing by this line, and 1 is passing by this line. Okay, so wherever you are connecting this one and this line, again this line is connected, this line is connected, and this one is connected to 0. So this is also 0, this is also 0, sorry, this is 1, right? This is 1. Okay, we are giving 1 here, this is 1, and this is also 1. Whenever you are giving the data D1 and D0, D2, D3, so that is connected to second AND gate. Okay, this is second AND gate. This second AND gate output, what I am getting here, D0 into D1, D0 is directly given to Q0, Q0 output, whatever the Q0, F0 flip flop is there, D0 is given directly. Okay, that is not depends upon any AND gate operation. And then this output is given to here. Okay, it is moving to the data, so that is shifting the data or loading the data, that is the main concept here. Okay, here 0 is connected, then 0 into anything is 0, this output is 0 here. Okay, and then here d1 into 1, I am getting the output is d1, then d1 plus 0 is d1 I am getting here, then my data is loaded into f1. Okay, similarly 0 and 1 I am giving here, 1 into d2, here d2 I am getting, here 0 I am getting, and then d2 output is getting, that d2 is connected to here f flip flop 2. Okay, that is loaded the data. Again d3, d3 into 1 I am getting d3 here, this is 0, sorry, this is output I don't know, and then this is 0, 0 into anything is 0 output, and then this connected to OR gate, so this is OR gate. Okay, remember this is OR gate. Okay, so then d3 I am getting, then in first whatever the 0 I am giving, this mode operation decides that I am doing load the data into the registers or shifting the data into the register. Okay, so 0 I am giving the mode. Whenever mode is 0, then it is acting like a loading the data. Okay, now I am giving the mode equal to 1. Okay, this mode value I am taking 1 here. Okay, then whenever 1 I am giving, shifting the data here, because here I am getting 1, here I am getting 0. If it is 0 means all the AND gates 2, whatever the second AND gates are there, all the outputs are 0. When mode equal to 1. Okay, if you are giving mode equal to 1, all the second AND gates are zeros. Whenever mode equal to 0, second AND gates are 1, data value we are getting. Second AND gates are data value we are getting. Whatever the data you are giving, that data value is coming from the second AND gate. Okay. So then whenever mode we are giving here, okay, mode 0, mode 1 we are giving, the first AND gate is there. The first AND gate is loaded, shifted the data. That means the Q0 is replaced with D1, and then Q1 is replaced with D2, and Q2 is connected to D3. Okay, so in this way the data will be shifting. Okay, so then first data I am loading here 0 1 1 0. Okay, so then the values will be coming like this. Okay, 0 1 1 0, the data is loaded initially. After that, from the next clock cycles, mode equal to 1 I am giving. From that conditions, it is shifting the data. Okay, this 0 is shifted to D1, and then this 1 is shifted to D2, and this one is shifted to D3. That means Q3 is 1, Q2 is 1, Q1 is 0, Q0 is 0. Okay, after that again shifting one for loading, one clock cycle is required, and then shifting, four clock cycles are required here. Okay, that is parallel in serial out. See, that is the operation. Whenever signal is 0, okay, loading operation is done. Whenever signal is 1, shifting operation is doing that. And then universal shift register. What is that universal shift register? Universal shift registers are doing all the register operations, like whenever giving the select lines 0 0, no change operation we are doing that. That means every whatever the data is there, same data is getting at the output data. Okay, that is clearing the data here, no change condition. So reset state only, it is taking that. And then whenever it is 0 1, it is doing the right shift operation. 1 0 doing the left shift operation. 1 1 parallel load operation. So all the operations are doing here only. That is the universal shift register operation. Okay, just see. So this is the circuit diagram, logic diagram here. Just check this multiplexer. This is 3. So here I am taking 4 by 1 mux. Okay, I am in this 4 by 1 mux, 4 inputs I am taking, and then 2 select lines. Based on these 2 select lines, that is S0 and S1, we are getting the output, that is data is loaded into D register. Okay, D flip flop. What it is doing? See, initially I am giving for 3, whatever the data I am giving, so that data I am giving here. Okay, so D3, D in 3, D in 2, D in 1, and D in naught. That is connected to mux, third pin. That means the select lines both are 1 1. Okay, what it is doing that? Parallel load operation. That means whatever the data I am giving here, every time the data will be coming here, and then data output is coming here. Okay, so the third input I am giving here, and then so the data will be loaded to D, and then data is coming out from the output. Okay, here also data is coming giving here, and then data is output coming here. That is parallel load operation. Okay, so parallel load operation means parallel in parallel out. Okay, and then shift register serial in serial out. Okay, and then again, what is the second operation? See, second bit is connected to which one? So this is connected to this line D2. That means it is doing the left shift operation. See, it is doing the left shift operation. D2 is connected to D2 is connected to D3. That means Q2 output is connected to D3. Okay, so Q2 output is connected to D3, and again, what is the connection here? Second pin D1 is connected to, again, what is the output? So 2, and then D0 output is also connected to what? again 2. Okay, see how I am connecting here. The first output is connected to second input. Okay, and then second output is connected to third input. Okay, third output is connected to, okay, third output is connected to fourth input. Then it is doing the left shift operation. So 1 0, what is doing, left shift operation is doing that. Clear? So 1 0, I am giving that selection. That selection is connecting to left shift operation. And again 1 0 condition, 0 1 condition. So 0 1 condition, it is connected to which one? One is connected to serial input. Okay, data input I am connecting here. Okay, this data input I am connecting, and then output I am getting. This is the output. That output is connected to which one? So this output is connected to again one. That is serial in, serial out. That means shift register, shift right operation, it is doing that. That means first output is connected to second input. Okay, then this output is connected to, again this output is connected to which one? So again third input. Okay, this third input, again third output is connected to fourth input. Then it is acting like a shift register. Okay, serial in, serial out, right shift operation, it is doing that. Are you along with me, guys?
Yes.
Huh. Again, this output is connected to value D out. Okay, after that, no change condition, 0 0 you are giving. Okay, this is 0, that is 0 operation. So this 0 operation, what it is doing that? 0 means where we are connecting. Let's see. So then D out, whatever the D naught output is there, that is connected to 0. So again, D1 output is connected to 0. Okay, so everything is connected to 0. That means the output will be remain same. Okay, so that is the no change operation. That is loaded condition operation. Okay, so initially whatever the outputs are there. Okay, so suppose you are doing all are zeros, then it is all the flip flops are zero only, it is doing that. That is the universal shift register. Understood? So parallel operation, shift right operation, shift left operation, how it is doing that. Okay, next, counters. What is the use of counters here? Suppose I want to do some clock pulses. How many clock pulses are required? So how many clock pulses are taking to complete one transaction? Okay, so that count I want to maintain. For that, we are using the counters here. Okay, see, registers that runs through prescribed sequence of states. Okay, so depends upon the application, that input pulses are called as counter. That means I am having shift registers. These are the shift registers. Okay, so these shift registers are connected to clock. Okay, this clock will be whatever the data I am giving here, data in. For this output is getting, right, whatever the input I am giving, that output I am getting here. So one clock cycle is required, two clock cycles are required, three clock cycles are required, I am saying that. Okay, so based on that counters, in these counters, these counters are divided into two types. Okay, binary counters, that means ripple counters, and then synchronous counters. Okay, ripple counters means whatever the output we have. Okay, see, this is the four shift registers I'm connecting. Okay, so this will be ripple counter, I told you, rotate operation. Okay, so this ripple counter is doing that. The last output is connected to the first input. That means entire the operation is rounding on the circular loop. Okay, so that is the ripple counters. In this ripple counter, twisted ripple counters are also there. That means Q is connected to input is ripple counter, that is also called as ring counter. Okay, and then twisted ring counter is called as q bar is connected to D input. Okay, that q bar is connected to D input. It will, that is also called as Johnson counter. Okay, so ring counter or ripple counter, that is that means, so here first input I'm having D1, I'm getting the output Q1, then this Q1 is connected to D2, I'm getting that Q2 output, this Q2 is connected to D3, I'm getting the output is called Q3, and then Q3 is connected to D4, and I'm getting Q4 output here. Every time I'm connecting the clock. Okay, so every time I'm connecting the clock here, here also I'm getting the clock. Okay, this is clock signal, and then see, this output is connected to input. Okay, that means every time you are getting 1010 data you are giving. Okay, this 1010 data I'm giving, so this 0 is coming out, and then 1 0 1. Okay, so then this empty position is replaced with again 0 here, because this 0 is coming here. Okay, so then n bit counter, see how many clock cycles for required to place all the data means 4 clock cycles are required. That means n bit counter you can take means n clock cycles are required, but Johnson counter 2n cycles are required. Why 2n cycles are required means the complement output I am connecting here. So the complement output means, so q is 0 means q bar is 1 I am getting. This one placed here, and then coming out once the loading data is required for ring counter is 4 clock cycles are required, and then Johnson counter is required means 2 into 4, that is 8 clock cycles are required. Okay, so how many what are the counters are there? See, counters are asynchronous ripple counter and synchronous counters. So asynchronous means the first output is connected to second input. Okay, that is the asynchronous counter. Synchronous counters means each and every one is having their own clock. The clock is the system clock is connected directly to the clock input, so all the flip flops are having the clock here. Okay, but here not like that. External clock is connected to the first flip flop, and then the clock output, first flip flop of the clock, then clock input of the LSB bit is the first counter. Okay, so that is the first counter. Then subsequent counters, the clock input is derived from the output of the preceding stage. I told you now. So the output is connected to, then here how it is connected the synchronous counters means, so this is my data input. Here only I am connecting the clock. Okay, here only I am connecting the clock. I am getting the output is called Q1. This is D1. This output is connected to clock. Okay, this clock is derived. This is the system clock. Okay, this is the system clock. Here is not like that. Every counter is connected to system clock. That means every flip flop you are considering flip flop 1 2 3 4, each and everything is connected to individual clock. That is the asynchronous counter, and then here we are connecting that data in, and I am getting the output Q4, Q3, Q2, Q1. Here it's not like that. Okay. See, here the asynchronous counters are two types are there. Either synchronous also there, up counter and down counter. Okay. Up counter and down counter, how it is connecting means, in this asynchronous, up counter is connecting like this. Okay. First input is there, right? Data input. Then output I am getting Q1, and then this Q1 is connected to this flip flop, next flip flop. This is the derived clock. Okay, see how it is flowing, the step down. Okay, that is the down counter connection. Okay, so this is the down counter connection. And similarly, so this is one flip flop and this is another flip flop. Okay, so this q is connected to the connection is down counter, and then q bar is connected to clock. Okay, this q bar is there, this is connected to next flip flop, that is the derived clock. This is called a step up, so this is up counter. Okay, so the first flip flop Q bar is connected to the derived clock of the second flip flop. This is the up counter. Okay, and then the first flip flop is connected to. So this is normal positive operation. Okay, so positive operation, that means active high operation. It is called that. Okay, all are connected normally. This is active high, normal operation. Similarly, active low means, so up counter, down counter is working like this one. So Q bar is connected to the next flip flop input. This is down counter. When it is down counter, this is negative edge prepper. Okay, neg edge, triggered operation we are taking as a q bar is connected to the clock, that is the down counter, and then pause edge, this is the positive edge. This positive edge means q1 is connected to the clock, that is the down counter. Clear? So the difference between the pause edge and neg edge, so pause edge normal operation, neg edge means reverse operation. Okay, synchronous, there is no problem in this up counter and down counter, both are connecting same. Okay, so because individual clock is there, right? And then ripple counter, up counter, down counter, up down counter. So how it is connecting, so simply every time the complementing the outputs we need to take means, so t flip flop and jk flip flop you can consider that, and you don't want to the complement output, so the d flip flop with the complement output is connected to the next d flip flop, so that is used. So most of the times we are using that d flip flops only, because this d flip flops is connecting the is giving the whatever the input we are giving, that only getting the output side. Okay, that is the reason most of the times we are considering the D flip flops. See, this is the up counter. So synchronous up counter. This is that. How I'm saying that synchronous. Sorry, asynchronous counter. Asynchronous positive edge triggered. Okay, asynchronous positive edge trigger. This is connected to serial connection. See, JK flip flop both are connected to one means every time toggling is there. Okay, toggling operation, that means q0, q1 and q2. How we can decide means, see, 1 1 I'm taking initially, the values are zeros, all are zeros. Okay, all are zeros, and whenever that q1 and q2 jk values are giving zero ones here, that value will be toggled. So whatever the toggling condition here, 0 is giving, I'm getting 1 here. Okay, so that one, and then q bar is connected to this one, this is the up counter. So q bar is connected to this one is called up counter, otherwise q naught is connected to this clock means that is down counter. Okay, that is the basic difference. And again, so q naught is toggled, and then this will be 1, and q1 is also toggled, so 1 I am getting here. Okay, so then here what is the output I am getting, q naught is 0, because previously output is toggled output 1, and then next clock cycle, say it is also toggled. Okay, 0, and then second third clock cycle q2 will be toggled. Okay, so q2 will be toggled, and then q1 q0 will be 0, because both are ones previous cycle, the next cycle is 0. After that, and then next cycle, the q2 will be see, whatever the output I am giving Q2, so this will be same, and then Q0 will be toggled here. After that Q2 will be toggled here, and then so Q3 will be same. Clear? How many clock cycles are required? This is the initial condition: 1, 2, 3, 4, 5, 6, 7. Okay, start from 0, then 8 clock cycles are required here. Okay, these clock cycles are counting here. That means all the values I need to place 1. Okay, so all the output should be 1 I need to place. That is the reason I am toggling each and every time. Okay, that is the up counter, binary up counter, 3-bit up counter. If you want to design 4-bit up counter, you can take the other condition. Okay, and then sometimes modulo counters are there. So modulo, module 10 counter, module 16, module 32, or module 6, or module 4. In this way they will ask you, so for modulo 6 how many flip flops are required to design. Okay, so here 3-bit up counter, you can easily consider the 3 flip flops. But what is this modulo? So this modulo defines that capital N. Okay, so small n greater than or equal to capital N. Okay, so then this n represents the number of flip flops. How many flip flops are required? Okay, so then 2 power n greater than or equal to modulo 6 I am taking, then capital N equal to 6. So because modulo 6 I am considering here. Then how many flip flops are they taking depends upon this n value. Suppose n equal to 1 you are considering 2 power 1 greater than or equal to 6. Is that condition correct? Wrong. Okay, so then n equal to 2 you can consider 2 power 2 greater than or equal to 6. Okay, 4 is greater than or equal to 6, condition wrong. And again 2 power 3, 2 power 3 greater than or equal to 6, then 8 greater than or equal to 6, then 3 flip flops are required. Based on that we can say that. So now tell me, the modulos 10 I am designing, how many flip flops are required here? Modulo 10 I am calculating, that means 2 power n greater than or equal to 10. How many flip flops are required? Tell me, anyone from the bridge. Are you guys are there?
Okay.
Tell me, how many flip flops are required for modulo 10 counter? So 4 flip flops required, right? So 2 power 4 greater than or equal to 16. Okay, sorry, 10. 2 power 4 is what? 16, right? So just up to 3 you can considered means. So previously we have calculated, right? Up to 3 you have considered means 8 greater than or equal to 10. Condition wrong. Okay, 6 is changed to 10. So 2 power 3 greater than or equal to 10. Condition wrong. Then 2 power 4 greater than or equal to 10. So then 16 greater than or equal to 10. So then 4 flip flops are required. Okay. How to design that modulo 10 counter means, this is the modulo 10 counter I want to consider here. Okay. So this is mod 10. That means from 0, 4 bits I am considered 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, okay, 0, 1, 0, 1, 0, double 1, 0, 0, triple 1, 1, double 1, triple 0. So 1, 0, 0, 1. Whenever it is reaching that 9 and then 10th position, it is again going to 0. Okay, so that is modulo 10 counter, because 0 to 9 is the counting is 10. Whenever it is reaches to 9, my output is getting 1 here, and then it is moved to initial condition 0. For that reason, we need to design the four flip-flops here. So these are the four flip-flops. All are connected to clocks. This is clock. Okay. Each and every one is connected to clock. Individual clock is there. Okay. So then here I am giving the data input 1, Q1, and then this is connected to, so D1 and Q1 is the output, D2, Q2 is the output, and D3, Q3 is the output, D4, Q4 is the output. Okay, so then here where we got ones here, the last final condition, Q, this is Q1, Q2, Q3 and Q4. So Q1 and Q4 is connected to 1 whenever Q1 and Q4 is 1 here. Okay, sorry. Q1 and Q4 is 1 here, that is connected to NAND gate. Okay, so these two are connected to NAND gate and it is connected to reset. Whenever it is sees that Q1 and Q4 is ones, and again it is resetting the flip flop. Okay, clear how I am resetting that? So this is the reset, this is the reset, this is the reset. Clear? So why I am connecting Q1 and Q4 is connected to 1 here means, so both are connected to ones, then I'm connected to one AND gate, it is resetting the operation. Okay, when it's because 1 and 1, 1 bar is 0. Okay, this 0 is giving here 0 is means reset operation is active low, then entire counter is reset to 0. Okay, that is the reason it is going to again 0. Okay, so that is the modulo counter. Okay, modulo 10 counter. See, this is the 3-bit synchronous bit up counter. So up counter means starts from 0. Okay, and again see how it is moving, 0 0 0. Next state is what? Next state is 1. Okay, present state is 0. Next state is what? 1. So the current state is 0. Next state is 1. And the next current state is 1. Next state is 2. And current state is 2. Next state is 3. Okay, current state is 3. Next state is 4. Okay, so that is the up counter. That means 0 up is 1. 1 up is 2. And then 2 is up going to 3. And 3 is going to 5. And 5 is going to 6. And 6 is going to 7. Then again whenever 7 is reaches that, it is going to 0. That is the state diagram I have shown here. 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, again 0. This is the up counter. Okay. So current present state is 0, then next state is what? 1. And then this is the present state, next state is what? Okay, 2. Okay, this way we are forming the present state and next state. Based on that, we are calculating the excitation table. Okay, so how you know the excitation table, what type of flip-flop you considered, based on that you need to consider the flip-flop excitation table. Here I am considering the JK flip-flop. So Q2, Q1, Q0, and then see here Q0 plus and Q1 plus and Q2 plus. That is the next state output. That means if you consider that Q0, then or Qn, this is the Q0. Okay, this is the Q0 plus 1. Okay, this is the Q2. Okay, Q1 and Q1 plus 1 and Q2. So the next state is Q2 plus 1. In this way, I will consider that. That means Q1 I am considering that the next state is Qn plus 1, Qn plus 1, Qn plus 1. Or if you consider that Q2 and then Q2 bar, Q1, Q1 bar, Q0, Q1 bar, you can consider that. Based on that Q2 and Q2 bar, okay, so these values, check that excitation table 0 0, what is the JK value? 0, don't care. So this Q2 K, J2 K2 0 don't care value, I got that. Again, so this is also same condition 0 0 0 don't care. And 0 1 case, 0 1 case, what is that excitation table? 1 don't care. Okay, so 0 1, what we need to write? So for, sorry, we need to consider this one, right? Q2 and Q2 bar. Okay, so not this one. So what is the condition here? This is 0 and this is 0. Okay, for that 0 0, 0 don't care. Again, this is 0 and again this is also 0, 0 don't care. Okay, Q2 is 0 and Q2 bar is also 0. Again 0 don't care. And Q2 is 0, Q2 bar is also 1. So 0 1 case is 1 don't care. Okay, that is the case 1 don't care and considering here. And then 1 0, okay, 1 1 case, 1 1 case don't care 0. Okay, don't care 0. And then 1 1 case, again don't care 0. Same previous state only. And again 1 1, don't care 0. 1 0, 1 0 means so don't care 1. Okay, don't care 1. Based on it, we need to calculate the J2 value, K2 value, J1 value, K1 value, J0 value, K0 value. So this is the K map. This is the K map. I'm finding the condition where we got ones for the J2. J2 is equals to Q1 and Q0, and then Q0, J0 equal to 1. I got that. Okay, because I am forming the quadrant here. Okay, for this quadrant I'm getting 1. 1 means what? Q2 bar and Q2. Okay, J not equal to Q2 I'm getting. Okay. Huh. Okay. See here Q2 is there and another two ones are also there, right? So then another quadrant we can form. After that all should be formed as octane. Okay, I didn't see this one test. Okay, so then octane form. Then here if you form the two quadrants also, that is Q2 bar. Okay, so Q2 bar plus Q2 is what is the output? One we get. One we will get. Clear? And then K2. So K2 also we will get that this is the K output. What is the output here? Q1 bar, sorry, Q1 and Q0. And then again the quadrant Q0 is the output. Again the octane here. See, these are the ones. All should be formed as octane. One, one we got. Same output I got. Okay, for J and K. So this is the 3-bit up counter. How we can form the counting value? See how it is connected to AND gate here. So Q1 is connected to AND gate, and then Q0 is connected to AND gate because J2 K2. What is the J0 value? J0 value, K0 value. One I am connecting here. Okay, and J1 K1 value, what is the output I am connecting here? Q0. Okay, this is the Q0 connection. Okay, how the J2 K2 will be connected? This Q0 and then Q1 is both are run together, then J2 K2 is connected. This is the reason we are calculating. See, previously modulo 10 counter, how I am connecting the NAND gate, the Q1 and Q0 is connected, sorry, Q3, Q4 and Q1 is 1, then my output will be reset, right? So here the output, how I am getting Q2 means, so based on this connection, see, inputs how I am connecting, J0 equal to K0 equal to 1, J1 K1 equal to Q0, and J2 K2 equal to Q1 Q0. Okay, these output equations are connected to inputs of the next flip flops. Okay, and then conversions we will consider that. Okay, so flip flops conversions also we will consider. Okay, where we are consider that conversions. So this is the flip flops, right? So how to convert these flip flops? Just one conversion I will tell you. Okay, I will explain one conversion. JK flip flop to SR flip flop I want to convert. This is the JK flip flop truth excitation table. First, we need to consider this is the truth table of the flip flops JK 00, 01, 10, 11. What is the output here? 00, no change. That means Qn plus 1 equal to Qn only. And 01 case means reset case. That is Qn plus 1 equal to 0, and 10 case means set condition qn plus 1 equal to 1, and 11 means toggle condition qn plus 1 equal to qn bar. Okay, that is the jk flip flop. For this I need to consider sr flip flop, sr and qn plus 1. Okay, for this SR, I need to consider that root characteristic table 0, 0, 0, 0, 0, 1, 0, 1, 0, and then 0, 11, and 1, 0, 0, 1, 0, 1, 1, 1, 0, triple 1. Okay, so this is the characteristic table of SR. Okay, so then what is that characteristic table? Tells that 0, 0 means no change condition. That means Qn plus 1 equal to Qn. What is the Qn value here? 0. Then Qn plus 1 also 0. Qn is 1. Okay, this is also 1. This is reset condition. Reset condition, what is the output I am getting? Only zeros only. Whatever the Qn plus 1 is there, Qn is there, I don't care about it. Okay, my output is 0 only. And this is set condition. Set condition is 1, 1 I am considered because Qn plus 1 equal to 1 only because set condition. Okay, and then invalid condition, don't care values I am getting. Then you can write the JK values here based on this excitation table. If 0, 0, Qn is 0, Qn plus 1 is 0. See, this is the 0, 0 case. Okay, this is the 0, 0 case. What is the value I am getting here? JK 0, 0. So 0 don't care. Okay, and then 1, 1 case. 1, 1 case is don't care 0, and again 0, 0 case 0 don't care. Again 1, 1 case. Okay, 1, 0 case. 1, 0 case. What is the value? Don't care 1. Okay, this is the 1, 0 case. Don't care 1. I'm taking the JK value. Don't care 1. And 0, 1 case. What is the 0, 1 case? 0, 1 case is 1 don't care. Okay, 1 don't care. And 1, 1 case again don't care 0. And so this is not considered, right? Okay, so don't cares only we will consider that. 1, 0 means don't care 1. Which one? This is the 1, 0 case. 1, 0 case don't care 1. Okay, 1. So for this J, you need to calculate the output K map. Okay, so J K map, how to calculate that? For J, 0, 1, 2, 3, and 4, 5, 6, 7. Okay, so this is S R Q N. Okay, so S bar, S, R bar, Qn bar, R bar, Qn. Okay, R Qn, R Qn bar. Okay, so again I need to place the values here. What are the values here? J value is 0. For 0 is 0. Okay, and then 1 is don't care. Again, next, what is the value I considered here? For 3, the value is see 0 don't care 0. For 2 0. For 3 is don't care, and then 4 is 1. 5 is don't care, 6 is don't care, 7 is don't care. Okay, so based on this, we here only 1 we got that. Then I'm getting the output J equal to S. Okay, So J equal to S I am connecting. And clearly, next K operation. What is the K operation I got? So 0, 1, 2, 3, 4, 5, 6, 7. Okay. So this is S and R bar Q bar, S bar S, R bar Q bar, R bar Q, R Q, R Q bar. Okay, where we got ones here. Don't care. Again 0 and then don't care. 2 is don't care. 3 is 1. Again here where we got ones here. Again. So 0 don't care, 0 don't care, 1, 4 don't care, okay, 5 is 1 and 6 is don't care, 7 is don't care. 5, this is 1, right? Which one is 1? So this is 0 condition, okay. So 0 condition, this is 1, okay. So 1 1 case and then 0 0 case, that is 2 and this is 3 and 4, 5, 6, 7. So fifth case, this is the fifth case, right? Fifth case, 1 1. 1 1 is don't get 0, right? Don't get 0. Then here the fifth value is 0 only. Uh, then fine. What is the output? So here 0. Then don't. This is the quadrant formation. Quadrant formation, and then k output is this is what the value r only I am getting k equal to r. Okay, so have you seen this JK flip flop how it is connected? See, this is the SR flip flop. See, S will be connected to JK flip flop. How I can convert this? Yes, K equal to R, J equal to S, and then K equal to R. Okay, J equal to S and K equal to R. This is the basic flip flop conversion, and then I am converting this. Just take this flip flop J, K, and then Q bar. Okay, so just I am connecting that J is connected to S and K is connected to R, like set and reset operation. Okay, so similarly, you can do the remaining operations. Okay, so remaining conversions you need to convert that. Okay, so now this is over. I think so shift registers, counter, triple counter, up counter, down counter. So then this is completed. Okay, whatever the remaining flip flop conversions are there, you can practice it yourself. So I'm binding these digitals.